We are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities, such as increased data privacy for users, reliability of service, high speed and efficient use of machine learning.
Today, machine learning algorithms such as deep learning use huge amounts of energy to power them. And as AI increasingly moves to low-power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation as possible out of every joule of energy. And Qualcomm has a long history of delivering technologies that do just that.
Our mission is to push the envelope of AI and machine learning in the areas that will significantly improve everyday life. We are asking challenging questions, like how do we preserve communication privacy? Can we use deep learning to compress videos? How can we eliminate uncertainty when making life and death decisions? And how can we use this knowledge to optimize Qualcomm chips that run machine learning algorithms?
Qualcomm AI Research is an inspiring environment where researchers collaborate, innovate, and share their findings with the world through high-impact publications. But we do so much more than just writing papers. We actually build AI solutions that are used in billions of devices. Your cell phone, your smartwatch, your drone, your car, and all the other innovative technology of the future.
So if you're interested in pushing the frontiers of artificial intelligence, machine learning or deep learning, and above all, if you feel passionate about the prospects of bringing ideas to life and impacting billions of people, then Qualcomm AI Research is the place for you.
Semua hal berangkat dari sebuah awal. Begitupun kami menjadi pionir. Memutar roda penggerak bangsa dan terus melaju. Kami hadir seperti sebuah keluarga. Dan terus fokus membangun perekonomian negeri. Menjadi yang terdepan, mewujudkan mimpi-mimpi besar. Dari atas awan kami terus bergerak dan berinovasi, melihat negeri ini tumbuh dan berkembang. Inilah kami yang tak akan pernah berhenti, mengantarkan Indonesia ke puncak kejayaan. Karena dimanapun dan kapanpun, kami selalu hadir melayani dengan setulus hati.
History, most of the time, is born out of the simplest of acts, just like the birth of our story, starting with the pursuit to close the distance through voice, and make exchanging of informations at your own fingertips. And who could have known that was just the first step of our long journey? We had to jump even higher, to open new dimensions of opportunities to explore the world. And we keep on transforming through different times so that we can bring joy and progress for all walks of life. The world is always spinning, just like the sun. Your loyalty in us has always been our light to keep on innovating. No more simple beginnings. Further and ahead, we have to keep on running. For you, for Indonesia, with the same vigor that has been driving us From the day one, we began. Our 55 years selalu ada untuk Indonesia.
Hello, everyone. Can you hear me? Okay.
I can hear you.
Okay. 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 We'll start now. Hello, Max. How are you?
Perfect. Thank you. How are you, Said? How are things going?
Oh, it's been perfect for the last 4 days. Thank you very much for your support. Okay, we will start. We are very honored to have you here with us today, and we are very sorry to interfere your vacation. For the information to all the participants, Max is giving the lecture from Les Hauts, I think the pronunciation may be wrong, a mountain in France where he spent vacation. So thank you very much for your effort. This talk will be shared to MLSS Indonesia participants and also for International Conference on Data Science and its Applications. Also here with us today, Rector of Telkom University, Prof. Adi Wijaya, Vice Rector of Telkom University for Research, Innovation and Partnership, Dr. Rina Pujiastuti, the Dean of School of Computing, Dr. Abdurrahman Baizal, and also the Vice Dean of School of Computing, Dr. Parman Sukarno. Now I will briefly introduce you to our participants, although I believe before this event, most participants have already known you. The slide. Okay. Prof. Max Welling is a research chair in machine learning at the University of Amsterdam and also VP technologies at Qualcomm. In the past, he held postdoctoral position at Caltech, UCL, and Toronto University. He received PhD under supervision of Prof. G. at Hoft. And yeah, of course, he directs 3 labs, machine learning labs in Amsterdam University. And yeah, he has lots and lots of scientific publication. So here, Max Welling.
Okay. So thank you, Said. Can everybody hear me? Since I am at a spot that might have spotty internet access, please let me know if my internet connection becomes bad. Or if you can't hear me anymore, just interrupt me and then we'll try to fix it. Yeah, so let me first say that I'm super excited to give these lectures and that this will hopefully be the first in a long chain of summer schools. And congratulations, Said, for organizing this. It's a big achievement, I think, and I'm happy that you decided to continue with it despite the COVID crisis, and hopefully next year we can do it live, and then I'll come to Indonesia. So I postponed my trip, and so for 1 year, so next year I'll be there. Okay, but I think this is a good start. Let's to do it online. I also wanted to make sure that everybody has a chance to interrupt when I give the lectures, to make it as sort of interactive as possible. I don't know precisely how to do it. We can do it through chat, and then maybe Said can, if there's questions coming up or something like this, you know, every, I don't know, 15 minutes or so, we can just answer a few questions. Or if you know, have the courage to just, you know, interrupt me while I'm talking, if something becomes truly unclear, that is perfectly fine as well. And so we can have a little bit of discussion. So I have a whole lot of material that I can cover, but I don't need to cover everything. I mean, that's the most important thing. So I'd rather have that whatever I cover is done well than then somehow I will have to finish everything, and then you don't precisely get what I say. Okay, so let's try that. Let me try to share my screen now. Okay, so can people see my screen properly now?
Yes.
I mean, if Said, yeah,
yes.
Okay, I can see you. So if you can, you know, thumbs up or something. Okay, so I'll just start my lecture now. Don't forget to interrupt if you don't understand anything, or otherwise Said will hopefully interrupt me every 15 minutes or so to have a little bit of a discussion. Otherwise, I just keep going, and that's probably not what we want. Okay, let's see. Right, so now I have a pointer. I hope you see the pointer too. And what I'm going to talk to you today is about deep generative models. Tomorrow I'll be talking about symmetries and graph neural nets and such. But today I'll be talking about deep generative models like the variational autoencoder. I'm sure you've heard of that thing, but also about flow models, a tiny bit about GANs, but almost nothing. And the running concept that you'll see is the free energy, or the elbow, which is, you know, the variational inference, which you'll find everywhere. That's sort of the running theme through the whole thing. And I hope you sort of will be able to understand and work with that object yourself and design new models using that tool. So here's an overview of what I want to talk to you about today. First, I'm going to talk a bit, it's sort of a high level, more philosophical sort of overview of discriminative versus generative models and why we should be interested in generative models. I'll talk about graphical models, which was basically the last, well, I would say, hype when I was working in the field. People have mostly forgotten about it, so I'm just trying to sort of remind people that that's actually very cool too. Then I'm going to talk about variational inference and expectation maximization as two algorithms that are at the core of the VAE, but also very interesting in their own right to know about. Then I'm going to talk about variational autoencoder. We're going to talk about normalizing flows. Then I'm going to talk about some more recent work, which is called the survey flow, which combines the two into one framework. So it's kind of nice if you have this one framework, because you can sort of, you know, understand everything in a unified way. And then the last part is neural augmentation, but I don't quite think I will get there. If things go well and you will ask your questions, then I hope I will not get there. But it's sort of my backup slides, so that you know, if things go very fast, that I still have something to talk about. And then I'll conclude. Okay, so at the very core of machine learning, there is this thing, this one equation, which you should really try to understand, which says that inductive bias, which is your prior sort of knowledge about something, plus data are being combined in order to make predictions. And they're on a scale. So for some problems, there's a lot of inductive bias because and very little data. And if your inductive bias is very good, then, you know, you should be able to build good predictive models. Where on the other hand, for some problems, there's a huge amount of data, and the domain is very complex, and the structures are very complex, and no amount of inductive bias will sort of be able to compensate for the data, in the sense that the world is far more complex than we can imagine or write models down for. And in that domain, actually doing predictive modeling using data models is much better. So there's this spectrum, and on the one side of this spectrum, there's sort of deep learning, mostly discriminative models, but increasingly also more generative models, where there's huge amounts of data available. But since it's discriminative modeling, you really need to train it on a very specific domain. So it's basically, you train this model to do well on recognizing skin lesions or recognizing cars in traffic or something like that. But as soon as you get out of your domain, these models typically break down fast. And I think the best examples for where this really works well is language modeling and image modeling at this case, so image analysis. They are sort of spectacularly good. On the other side of the spectrum is the spectrum where we don't have a lot of data, and we need to rely on our inductive biases. And so that's where a generative model, where we can sort of put in variables that we understand and relation between variables that we understand, and other types of inductive bias, is actually going to be very helpful. And there's another really important reason why these types of models are expected to be helpful also for building more flexible AI systems, and I'll argue more later, which is because they do much better out of domain generalization. So you can train a model in one setting, one context, and then move it into a new context, and then it will still perform well. And humans are masters of this, right? We can learn something in one setting, and then we can generalize it into a completely new setting, and we can still use the lessons that we have learned. Like if you learn to drive your car in England, right, on the left-hand side of the road, and then you go to Indonesia, I don't know, do you drive on the left or the right-hand side? I don't know. But if it's on the right-hand side of the road,
right,
yeah, it's on the right. Okay, good. So then you have to sort of take your car and sort of drive on the right-hand side of the road with different traffic signs and all sorts of, and the roads are different, I'm sure, and you can still do well, right? And so that's amazing, and so that's hard for machine learning algorithms which are trained using deep sort of discriminative models. So what is a discriminative model? In a discriminative model, we take the raw data, think pixels in an image or audio samples, and we map it through a highly parameterized and maybe somewhat obscure parameterization that is very general. And then we train all of these connections, all these millions or billions of parameters. And then what we get out is basically a property, a high-level property of the system, or a class label for the system, or some semantic feature of the system, or something like that, right? So, and sometimes we do it in the opposite way as modeling typically happens, as I'll tell you in a minute, which is where you start from these properties and then try to generate sort of the things you see in the sensors. Here you start with the sensory data, and you try to predict properties of the system. So in deep learning, that's a typical example of, in discriminative models, at least, where this has been hugely successful. And of course, it led to the Turing Award in 2019 for these 3 people here. So it works extremely well on domains where we can collect many examples. It is, at this point, responsible for about 90% of all the progress and investment in AI, and it's creating a huge amount of business potential as well in companies. I mean, I work for Qualcomm, but it's the same for Google and Amazon and all the internet companies. They use AI and deep learning in particular in a big way. And you could still ask yourself the question at the peak of this hype, will it be the final answer? Will it now be a question of throwing more compute at it and more data at it, and we will solve everything? And here the community is highly divided, because on the one hand, it's success after success. And you've probably seen the latest results of GPT-3, which is a new kind of language model. It's like amazing what it can do. And sort of, if you're in that camp, and you believe that, just more compute and more data will do it, then this is a very positive data point for you, right? It will tell you, you know what, again, there's a lot of room to improve things by just scaling. There's another camp of people that says, no, actually, we need something else. And in particular, if we need to do out of domain generalization. I'm somewhere in between, I guess. I do believe we need something else. And I do believe that is more in the form of generative modeling of the world, as I will try to argue. So in a way, so the world is divided in sort of two camps, the Kirks and the Spocks. If you think, the Kirks are the people who are saying, machine learning is about intuition in a way, because if you think about neural networks in the brain, they sort of operate unconsciously. You take data in on your sensors. Without thinking, it will be processed through your visual and auditory sort of pathways, and you sort of learn to recognize and understand the world. On the other side, there is the Sparks who say, well, actually, you do need sort of high-level reasoning. You will need sort of symbolic AI and logic to be incorporated in all of this. And the left-hand side is not enough. We need to have bits and pieces of this as well. And in neuroscience, there is so fast thinking, which is sort of a deep learning type of thinking, and then there's slow thinking, which happens in the prefrontal cortex, which is more like the reasoning part. And so the question is, do we really need the reasoning part? Now, let me give you one example of where humans excel and where, at this point, neural networks are not as good as we would want them to be, despite successes like GPT-3. So here's a particular creature. It's called a water bear. And I'm going to give you just this one single example of a water bear. And we're going to test you on these 3 test examples. Now, you can probably fairly easily figure out which one is a water bear and which one is not. And the reason is that you have a lot of prior knowledge in which you can embed it, right? So in this case, this one you'll be pretty certain about. This one you'll be pretty certain about it's not a water bear. And here maybe you're in doubt, but you're seeing has the same number of legs. It has this funny snout, so you can probably think that that's a water bear as well. So you've trained yourself from one example. Hopefully you've never seen this creature before, but maybe you have, I don't know. Right? And so how is it that we can do this so well from one example? And the reason is that we embed this particular image in a sort of ocean of background knowledge that we already have about the world. We know the laws of physics, we know the laws of biology, that things have need to breathe or eat, and they have legs to move and things like this. There's psychology, not so relevant for this, obviously. Causality, sociology. There's all sorts of things we know about the world in which we can embed this knowledge, and so we can sort of learn much more from a single image than current deep learning systems can. And then there's this thing about causality, which is currently not really taken into account in our models, and that basically it is our sort of that if we can incorporate causal mechanisms in our models, we can achieve this generalization a lot better, because the causal mechanisms are really what's underlying. There's the reasons for certain things to happen. They're not mere correlations, but they're actually the reasons for things to connect in relationships. It's my strong sort of conviction that if we don't model causal effects, we will not be able to ever train systems that make optimal decisions. And so here's a quote from Judea Pearl, who also won the Turing Award. It's not the Turing Award, I see there, it's the Turing Award. So he said, this ingredient, by which he means causality, should allow computer systems to choreograph a parsimonious and modular representation of their environment, interrogate that representation, then distort it through acts of imagination, and finally answer what-if kind of questions, right? So what's happening here is that you can build representations which are modular, which is very important. So you learn something, and then this something can be applicable in multiple settings. It's not just true for this setting, but it's like a module that you can use in multiple settings. And then you can actually sort of imagine worlds that don't exist. You can think about, okay, what is it like for a pink elephant to unicycle on the moon, right? Which is something that will never happen. And it's also something that you will never see, but you can still conjure an image of that happening. And that's because you have a module of an elephant and a module of a bike and a module of the moon, and you can sort of put them together in a way. And you have causal causal mechanisms in your mind. Like if you move your, if you move your legs on the pedals, then your bike will move forward, right? So you have all these things, you can put them together. And you can imagine new worlds that don't even exist, and you can ask, what if I would do this, right? What would then happen in that particular world? And this way of being able to generate worlds and think about worlds that never exist, I feel is very, very powerful for AI. Okay, so then what is a very important ingredient for machine learning or for AI is this idea of generative or forward models. And so that's where we can put in the causal mechanisms and things like this. So a causal mechanism. So here's a generative model. A generative model simulates the data generating process, and so it goes directly in the opposite direction as the discriminative model. So here we start with the abstract features of the world, the properties, the classes of things, and then we generate the things we would see in the sensors of our sort of instruments. So here is a simulation of two galaxies. Again, something that you will never be able to observe in real time because the time is accelerated super fast. This takes billions of years. But we can still, using our laws of physics, running it in a forward generative direction, we can sort of simulate how that work will look like. And of course, we have simulators of earthquakes, of heartbeats, of weather, etc., etc. So these simulators are typically built using ordinary or partial differential equations, which is the tool that almost every scientist except machine learners uses. So this is the tool of all the other scientists. In machine learning, this has now taken, shape as probabilistic programs. So the simulators you can also build from probabilistic as a probabilistic program is basically a programming language where you can sort of, you can sort of specify precisely, how things relate and when you generate random numbers, and you can also do automatic inference in these systems. And then the graphical model, it's a sort of a language for graphical models, if you want. And sort of here is a bunch of graphical models. And the big difference of graphical models and deep learning is that every node here means something. So when you write down this thing, you say that this means something and this means something and these relations mean something. They're all very intuitive and interpretable. And that's quite different from deep learning, where everything it's just neurons that are not very interpretable. So what type of unsupervised sort of deep learning models do we have in the world? And this is perhaps the most sort of popular one, which is a generative adversarial network. And I'm not going to go into the math of this. I am later going into the math of VAEs, but again, it's very intuitive. And the way that it works is as follows. You start with, again, a data set, let's say, of images of dogs. And then you train a generator, which is a network, a generative network that takes in random noise, and then through transformations of a neural network, generates images. And then there is a discriminator, it's a second network, and the network takes in either a true data point or a generated to the pseudo data point. And this is just a neural network in the usual discriminative sense, and it will try to figure out whether this is a real or a fake network. And the point is that they are sort of have opposing sort of objectives. This one tries to be best at being so good that the discriminator will not be able to discriminate whether it was fake or true. And then sort of this discriminator fails. So the generator wants the discriminator to fail. But the discriminator wants to continually be able to discriminate these two things. And it's sort of like an arms race, if you want. And in this arms race, the generator will get better and better and better, as well as the discriminator, but it's the generator that gets better that is then able to generate pictures that are indistinguishable anymore from actual data. And here's a beautiful example. One of these dog images is fake, and you can just have a look at this. And 10 years ago, I wouldn't have thought that you could generate dog images that are so incredibly good and so incredibly realistic, and that don't look like an actual image, right? So it's not like there is an actual image. So I'll just first show you which one is the fake one. This is the fake one. Now there's no image in the data set that actually looks like that. So otherwise you could just copy it and overfit, but it's not. It actually has understood how you draw or how you make photographic pictures of dogs, and then it will just create that picture. So that's an amazing feat of a GAN, I would say. That's a really fantastic sort of achievement. Okay, so here's a different breed of generative models that I've been working on. And you can sort of think of these in two paradigms. There's, in the scientific literature, people use the words forward and inverse models for this. And sort of in the machine learning community, we use encoder decoder models. So what is that? So let's first start with some latent quantity of interest. Now this is an 8 that I don't have access to. It's a latent 8 that that I'm going to try to reconstruct by only looking at the observation, which is this. So this is what arrives in my sensors. And so I have a forward model that says if this were an 8, then there is this channel, this noisy channel that then produces this in my sensors. And that's what we call the decoder model, or the forward model, or the channel. And then the task that we are trying to, or one of the tasks, this is already pretty good that we can generate this, but the task that we're trying to achieve is to do the inverse, to say, if this is the observation, then what does the true latent image look like? So this is one of the tasks that you might want to solve. And in a variation autoencoder, this situation looks like this. So I have a sort of blurry image of the world. I send it through my encoder distribution, which then computes properties of this object here. Now, these could be abstract properties like the class label or the style in which it was written. But in this particular case, it's actually trying to reconstruct at pixel level, what is the actual image that caused this observation. And so that's the latent representation. And then from that latent representation, there's a decoder or channel model that takes that and produces the observations again. So we have a forward model or a decoder, which is P of y given x. And then there's an inverse model, which is P of x given y. Okay, now you can ask yourself, how are discriminative models and generative models actually related to each other, right? So if we have models, that generate observations given sort of abstract properties of the world, how is that related to the discriminative models, which say, well, give me the actual observations in the world and then generate class labels or abstract properties? And the so I would say the relation is extremely simple and fundamental. It's called Bayes' rule, which basically says that if I have my discriminative model for, say, class given data, then that should be equal to the generative model of data given class times a prior over classes divided by a normalization constant, which is the P of the data. And so in the generative world, I parameterize this object. I say, okay, I write down a model that takes in my Z values, which are my abstract properties of the world, and I just try to figure out how the process of data generation works. And in this world, this is a deep learning model. I parameterize this object, which is a deep neural network where it takes in observations and produces class labels. But at if this scientist who does this and this scientist need to talk to each other, so this is the way to translate between the two models. So what are then the pros and the cons of the two types of modeling? So on the left-hand side, this is the typical scientist, if you want, or the Spock, if you want, right? So it's a white box. It's very data efficient because the model uses a huge amount of expert knowledge. For instance, the laws of physics. And there's also few parameters to learn in these models. It's highly interpretable because every time we write down a variable or a relation, all of these variables mean something. So when I do inference and say, what's the value of this particular, unobserved random variable, then at that point, when I know it, it means something to me. Unlike a neuron activation, I have no idea what that means. And it's much better at generalization because it uses laws of physics, causal structure. So when I learn something in one context, I can then move it because it actually models the way the world works. I can then move it into a new context and it should still work because the laws of physics are invariant, if I would move them in one environment or the next. Now these kind of models, neural networks, are far more flexible, and what's actually more important, they are not limited by the human imagination. So if we write down models, they are always oversimplifications of the real world. I mean, we love to write down linear models, and we love to write down Gaussian distributions, and especially in economics and all these other fields where people always immensely simplify the world. Now, if we write down a deep neural network, we can put billions of parameters at it, and we're no longer sort of limited by the sort of human imagination. And that's also the reason perhaps why they are much more accurate. You model directly, you have a lot more freedom to model, and also you model precisely in the direction you want to predict, because you want to use these models typically by looking at observations and then predicting properties of the world. And they're also fast because, again, since the model is trained in the direction in which you intend to use it, you just push the data through your neural net, you get an answer. Where if the model looks like this, you have to do inference, and you have to use Bayes' rule to invert that model and get your sort of your class labels or whatever out of that. Now, both of it therefore have advantages and disadvantages, and in some sense, we want to build on the strengths of both of these models. Okay, so now we'll become okay. So let me just say at this point. There's three major streams of, I would say, deep generative models. There's GANs, there's VAEs, and there's flows. I will touch on VAEs and flows in the following. I've said a little bit about GANs, and I would say that GANs are at this point the more popular one. But anyway, we'll talk about VAEs and flows. Yeah, so this is a good time to ask some questions, maybe, Saeed.
Yes, there are some questions already.
Okay, good.
First, can you explain what is random noise when you explain about the GANs?
Right. Yeah, so here. So this basically means in order to generate an 8, you first generate, let's say, a random number. This could be from a normal distribution or from any distribution that you like. That this is your prior P of Z. This is the distribution over your random variables that you start with. And it should be a very simple distribution. And what this generator does is it basically morphs that distribution into a much more complicated manifold. So it takes that piece of basically a random image, which is completely random and drawn from a very simple distribution, and morphs that sort of completely random thing into a nice image of an 8 or a 7 or a 6 or whatever the domain is. So it basically maps the sort of the very simple distribution into a much more complex one. So let me just maybe go back to this on the first slide. I had this image, which I stole from Shireen El-Habian's web page, which I thought was a very beautiful image. But sort of here you can see how that works maybe. So you start with a very simple distribution, a prior P of Z0, and then you send it through some generative process, and then you get some far more complicated distribution, where everything here means something. If I pick this particular point, it's either a 4 or a 6 or an 8 or a 5 or whatever, right? And that thing should look like the actual data distribution. So I would say that, yeah, so this process going, so here's random noise, and going to this here is basically turning that random noise into an image of an 8, let's say.
Right. Next question from Yopi. Goldmine of research would be how the black box can do what the white box can do. Do you think so?
Yeah, so, but they're the inverse of each other. So in some sense, this is precisely what the VAE tries to accomplish, as I will try to explain. So the generative white box needs to be the inverse of the discriminative black box. And so as long as you can maintain that relationship, then I think, as I understand the question, that is precisely what we want to achieve.
Maybe last question before we continue. Are Gaussian noise the only type of noise that can be used as the input to the generator? Actually, you have explained it. And the next follow-up is also, can we use an image as an input and add noise midway through the generator?
Yeah, but it's not quite clear where that image would have to come from. So I would say it's much easier if you want to generate things to I mean, you can do class conditional things. So maybe if you want to say, I want to condition on a particular class, and I want to generate a mountain, then you could provide that information in the form of an example image or the form of a piece of text, basically mountain. And then you can ask your generator to only generate pictures of mountains, or you can sort of learn it to conditionally only generate pictures of mountains. But in general, I would say it's not quite clear where that input image would come from if you want to just build a generator.
Yeah. Right.
Okay. So maybe we continue now, or?
Yes, I think we can continue now, and then we will take a question later again.
Yes. Okay, good. Okay, so now we're going to go into more technical detail, and I'll start simple. Well, not simple. I start basic, let's say, to going back to the very basics of machine learning, and then I'll build more complexity on top of it. So I would say we never have to forget, we should never forget that machine learning basically is a form of doing statistics. It's not just doing optimization, and many people forget that. And so in general, the setup is that we generate data from a distribution P randomly. So that's our assumption, where X is input and Y could be labels or output, right? And we have some joint distribution over X and Y's, and we generate our examples from this random probability distribution P. And then we can sort of say, okay, now we have some objectives that we can try to maximize for machine learning, for learning machine. For instance, for unsupervised learning, I could say, okay, forget about the Y's. Let's try to maximize the probability of the data that I've seen under my model given some parameters. So my parameter should put density or probability mass on the data points that I've seen. Now, of course, that's very easy. I can just put spikes there. So, but that doesn't generalize, right? So I need some parameterized smooth density, and then I want to train the parameters data such that it will put more mass on the data that I've seen than on other places. Now that's unsupervised learning. There's also supervised learning, where I'm interested in fitting a conditional distribution. So given some input, let's say an image, I want to predict the label of that image. So there I want to maximize the conditional probability distribution of Y given X, typically the log for numerical reasons. and then I maximize over parameters theta. Or more generally, in supervised, I can also just define some arbitrary loss L that will look at the difference between my data point I and my sort of reconstructed label Y from X. So this here could be a neural network that takes in an image Xi and then predicts a label Y, and then I just look at basically the loss between those. Could be cross entropy or something like that, whatever you like as a loss or an error between these two labels, and then you simply try to minimize the loss. And then I guess the important part is that, clearly this is an optimization because we're trying to maximize over theta. But what's important is to realize is that, let's say if instead of this sample, I would draw another sample randomly, it would be an equally valid sample. And it would go through the whole process again of maximizing my parameters theta under some loss. Now, because the data was different, because it was randomly generated, I will get a different optimal set of parameters, right? So this set of parameters here, theta prime, for my different generated data set, but from the same distribution, is going to be different from my learned set of parameters theta on my first data set. Now, if I do this a whole bunch of times, I'll just get a whole distribution over these parameter estimates. And intuitively, it should be clear that there isn't much meaning in, trying to achieve more precision than what these differences are, right? So if these differences fluctuate at a certain scale, let's say that the third, decimal point is fluctuating up and down under resampling of my sort of data and then re-estimation, then I shouldn't try to nail the fourth and the fifth and the sixth decimal places of this theta, because it's meaningless, because if I would have had another data set, it would have changed anyway. And so overfitting basically says that you're trying to nail down these higher order decimal places of this parameter. And if you just consider learning as an optimization problem, you would be happy to do that. If you consider it as a statistical problem, you would realize that that's meaningless. In fact, it's harmful because now you're overfitting and you're not going to generalize very well. So I think that's something that people have to really keep in mind when they think about, even deep learning problems. They're nowadays just viewed as optimization problems, but don't forget that they're actually statistical problems. And I guess one of the most important sort of equations or sort of ideas around machine learning is this bias variance trade-off. You can understand a lot of issues in machine learning by understanding the bias variance trade-off. Now let's first build some iteration of what bias and variance are. So if I'm going to try to throw a dart in this target, if I have high variance, on average, I'm pretty good, at sort of finding the red target, but they scatter a lot. So I have high variance. But if you compute the mean of these, they're right in the middle here. If I have high bias but not so high variance, there's something wrong with my way of throwing, I guess. And I'm always sort of outside of the red dot, but very consistently. So this is a high bias. This could be because my model is too small or something like this, right? I'm doing linear regression where my model is really, quadratic or something. This could be because my model is very flexible, and every time I redraw the data, I'm going to get a different answer. And of course, you can have high bias and variance, which is even worse. And the best situation is if you have low bias and low variance. Now, if you look at how you can easily decompose your prediction error, so you can do the bias variance trade-off. So how does that work? So you take, let's say you're trying to do a regression problem. You take your input random variable x, which is some number on the x-axis, let's say, and have some nonlinear function f that would produce my y value. And there's some noise added to this process because the labels that I get are not the actual true labels, but they have some noise. And it's drawn from some normal distribution. Now I can study the error. And the error is how well There's my predicted function. So this is, after I'm doing maximum likelihood estimation or whatever, I'm getting some predicted function f of x. How well does it match my y, my data labels y? And that's the error I want to minimize. And I can decompose that, after some math, into 3 terms. The first term is the bias squared. And that says, on average, all of these estimates, on average, how different are they from my function f? So that's kind of here. If I take the average of all of these dots, right, then that's sort of some dot in the middle. And then the question here would be, how far away from the center would it be? There would be this term. So here it's very high bias, this distance here. So this is the variance, which is solely computed in terms of the actual estimate. So this is hard to compute because you don't have access to f. But here, this is only computed in terms of f hat, which you have access to. So here, this is the variance of the the estimated function f. And that's kind of the scatter here that you have. Like, what is the scatter around this true value here? And then the last one is actually what we call irreducible error. This is the error in the labeling process. So there's no way you can get better than that. So we call this irreducible error. And these 2 terms together are sometimes called epistemic uncertainty, and this term is called aleatoric uncertainty, so now and then. And then, of course, there's this sort of epic plot that everybody shows. So, and it's actually wrong at this point because there's something on the right. People have figured out there's something on the right here, I'll just quickly say. But here's the error, which is this here, and here's the model complexity. So here I'm going to throw more and more and more parameters in my model. Now the bias is going to go down, because as I have more and more parameters, I'm going to be able to, on average, to model the true function f better and better. So I'm going to be in this situation, but as I throw more and more parameters, the mean of these points are going to get better and closer to the true value. So I have less bias, like here. But then the variance is going to be up, because as they have so many parameters, every time I redraw a new data set, what will happen is that I will just get a very different set of parameters. And so the variance in these predictions will go up. And there's something in the, some optimal point in the middle here where you have the minimum amount of complexity. Sort of the minimal error. And sort of, this is the regime where you overfit, this is the regime where you underfit. And this is the optimal place where the total error is minimal. And so there's a trade-off between bias and variance terms. Now, these days, people have figured out that for deep learning, what's happening is total error goes up. And then at some point, when the training error goes all the way to 0, the curves are coming down again. And there's a very interesting story that you should, maybe read up on yourself. But this is now somewhat old, because people have figured out for deep learning, there's something on the right here where with more and more and more parameters, actually with the proper type of regularization, your error can start coming down again, which is very interesting. Okay, I'll talk a little bit about graphical models, which is sort of something that we did before the deep learning hype, but I would say that it is actually it is very important for when you think about generative models. And in a graphical model, it's basically the way that people, scientists, model their domain, like an economist or a biologist or something like this. Which means that you put some random variables together, which every random variable means something. And also they are put together in a way that even the relation means something, right? So in this case, this is a model for traffic jams. And it basically says rush hour, bad weather, and accidents, they all are causes for traffic jams to happen. So imagine that these are actually causal connections now, right? So note that I'm using causality now. Now bad weather, but bad weather also causes accidents. So there's an arrow here too. And then sirens, of course, they are caused by accidents. So here's a little graphical model, and you can write down what the joint probability distribution for all of these variables is. And you can write them down in these conditionals. You can say it's a traffic jam given these 3, so it's probability of traffic jam given rush hour, given bad weather, and given accident, times the probability of sirens given accident, times the probability of accident given bad weather, times the probability of bad weather, times the probability of rush hour, right? And you can now, and the magic is that you can compute every possible independence relation here from this, or either from the graph or from the equation. So for instance, I know that rush hour and bad weather should be two independent random variables. They have nothing to do with each other. And from the graph, I will show graphically, you can show that that's true in this model. But also you can say, well, how would that happen? Well, it would mean that I've taken my joint probability distribution and I marginalize, integrate over all the other variables in the model, and then look at the probability distribution over rush hour and bad weather. And that should factorize into the probability of rush hour times the probability of bad weather. And that means that these two, in this model, these two random variables are independent of each other. But there is a much nicer way of graphically seeing all of these conditional independence relationships. And that's called the Bayes-Bol algorithm. And the Bayes-Bol algorithm basically says there's a couple of rules in which you can sort of pass a ball through the network. And if you can pass a ball through one node to the other node, these are not conditionally independent. These random variables are dependent. But if all the paths between these two random variables are blocked and that you cannot pass the ball, then the two random variables are actually independent. So here's the rules. For instance, this rule here says that if this is not observed, this random variable, so we're not conditioning on this random variable, then the paths here are blocked. Now that's precisely saying in this model that rush hour and bad weather, they are going to be independent given traffic, not given traffic jam, but if this traffic jam is unobserved, then these paths are all blocked. So you cannot get your ball from here to here in any way, which means that marginally these two things are independent of each other. And this is another interesting one, which is called explaining away, which says that if you actually observe this thing, then the ball can pass. So this means if I would observe there is a traffic jam, then suddenly rush hour would become dependent on weather given the traffic jam. Now that's very subtle, but it has to do with the fact that the fact that I observe traffic jam tells you if the rush hour is the most likely explanation, then it tells you something about the probability of bad weather as well. And so these things become correlated due to the fact that they observe traffic jam. Okay. There's another breed of probabilistic models, which is called Markov random fields. These have undirected edges, like here, and the conditional probability relations are very intuitive. It says that given that I observe these two, all the paths are blocked that go through these nodes, so I can't get from here to here. So my Bayes-Bol would always bounce here, would never get through, which means that these nodes are independent of these nodes given these nodes. And so because the edges are undirected, the rules for the Bayes-Bol are very simple. You can also write down a probability distribution that would satisfy all these conditional independence relationships, which is called this here, which is the product over maximal cliques in the graph, which I will explain in a minute, of some potential function, positive potential functions psi, and then we normalize the whole thing. So what is a maximal clique? Well, a maximal clique is the largest completely connected subgraph. So in this case, it's a triangle here, and here it's an edge, right? Because these things are not connected, it's not these four nodes because they're not maximally connected, completely connected. So you write down all these blocks, these three and this pair, and then this pair, and then this pair, etc., or these triangle here, and you have some potential positive function of the random variables in this block, and you take their product and you divide by z, and then you train, for instance, the potential functions here. Then if you write down like this, then all these conditional independence relationships that I just explained using this Bol algorithm, they will hold under this parameterization. And that's called the Hammersley-Clifford theorem, which says that for if the probability is larger than 0 for all x, then all conditional independencies in P will match those conditional independencies in the graph. Now there's one breed of very important latent variable models, which is this particular, it's a graphical model, it's a directed model, it's a Bayesian neural network, where I have some unobserved random variables z, and I have a prior p of z over those random variables. And then I have a conditional distribution of x given z, which is p of x given z here. And then the p of x over the things that I am interested in here, because I'm going to get data on these nodes, is basically you have to marginalize over everything that's unobserved z. So I get the probability of x given z, p of z here. So this is a very important breed of models. In particular, it's the decoder model in a VAE that we will need. Okay, so once we have graphical models, we also need a way to do inference in these graphical models. And there's basically two kinds of inference that people do. One is called variational inference that we will discuss in this lecture. And one is called MCMC sampling that we won't touch on in this particular lecture. And what do we do with variational? Well, we say P is too complicated. So let's define a class of probability models Q that is tractable, like Gaussian distributions. And let's find the closest in this class to the intractable P. And so that this becomes an optimization process of finding this particular point here, which is the smallest distance to P under some distance metric, which is the KL. In MCMC sampling, we're drawing random samples from this distribution. We have some procedure of drawing these samples sequentially. And then if we wait long enough, then in fact, and we draw enough samples, then we can sort of characterize the distribution in increasingly more accurately without making an error. So this model is deterministic, and so it's optimization based, which is therefore convenient, but it's biased because you will never be able to model P because you'll always be outside of this P here because of this approximation that you're making. On the other hand, it's easy to access convergence because it's just optimization. And there's many local minima in this problem as well. So it's hard. The optimization is actually hard. In this process, we are sampling stochastically. This is a stochastic algorithm. It's unbiased in the limit. So in some sense, you can control the error by keep sampling. So the longer you wait, the better it gets, where that's not true here. It is hard. If you have two modes, it can take exponentially long to move between two different modes. And it's hard to assess convergence, unlike here. So both have advantages and disadvantages, and people have written down hybrids of these as well. But we'll focus on this and hope and make this class as big as possible. In fact, we'll make it so big using deep learning that hopefully it touches very close to the speed. Okay, this is probably another good time to ask some questions, Said, if there is any. So we can't hear you yet.
Yeah, the first question is regarding the last slide about the variational inference. Why is P outside Q?
Right. Well, P could be an arbitrarily complex distribution, right? Because it could be let's say, the Bayesian inverse of a generative model that is very, very complex. And it could depend on, in a discrete case, it could depend on an exponential number of terms. So it's just, because our models get very sophisticated and complicated. For instance, when we compute in a posterior distribution over some random variables, then this distribution can become very, very complex. And Q is a set of distributions that I am choosing myself. So I just say only Gaussian distributions or something like this. So it will never be able to completely fit P, but I'm going to try to find the best one. And I will explain to you how we do it in the next slide. So there's details on precisely how you would do something like that.
Right. You said before that from your previous picture that if now the model becomes too complex, the error will eventually go down again, right?
Yeah.
Is there any intuitive explanation about that?
Yeah, there is. Well, I'm not sure it's intuitive, but it has something to do with the fact that if you think about interpolating between points, if the number of, so think about some kind of polynomial. So if you try to interpolate between points, then there is a point when the number of data points and the order of the polynomial is equal, that you can go through every point. So your training error will actually be 0. But if you plot it, you'll see that it will go, these curves will go up and down. They all swing like crazy to get through each one of these points. Now, if you would increase the order of the polynomial further and further and further, then, and you put some regularization on the norm, let's say, of these weights, then it has a much easier time getting through all the points in a way that is much smoother. So it's not forced to go up and down because the order is precisely equal to the number of points. It's just very hard for it to get through all the points, and it's have to swing up and down. But if it has a lot of degrees of freedom to model this, it's much easier to go through all the points. And then if you say, well, I want from that set of functions that goes through all the points, I want the ones where the norm, let's say, is very small of the parameters or something like this, then it will create a very smooth function, the smoothest possible function, let's say, that goes through all the points. And somehow that process helps you in deep learning, where there is a huge number of parameters, many more than data points often, and you also apply a lot of regularization, will help you again to, to generalize a lot better. And to just focus in on those functions, like the smooth functions that actually generalize well.
Maybe the last questions for now.
Yep.
How to build the optimal Bayesian network if we don't know the relation of each features in the data?
Yeah, so I guess we can probably answer that by going to the next slides, because the VAE is sort of trying to do that, right? So it's
right.
Yeah. Let me just continue now, and then hopefully that becomes clear. Otherwise, ask again.
Of course. Yeah.
Okay, so then the next part of this talk is going to be about basically how to train these decoder models, these models which produce let's say these generative models that generate the data given some latent features, which is the P of X given Z times P of Z. So P of Z would be, again, this sort of very simple distribution over my latent variables, like the random noise thing in the GAN as well. It's the same here. And then the P of X given Z, that's where all the work is. It's kind of some deep neural network that then takes that random input vector and transforms it into an image or an audio signal or something like this, which is like the data we observe. So this is our interpretable generative model. And what we will do is, so we will write down a bound, which is it's the log probability of X of the observed data. And there is this bound which is called the elbow, which upper bounds it, and it has this additional random distribution Q in it. And Q is of some tractable set, and in the VAE, the tractable set is going to be something that we can quickly fast sample from, which is we can still be very complex, but the only thing we will require is that we can draw a fast sample from it. In the older literature, this Q is like a normal distribution or some distribution that we can actually integrate over analytically. So let's first focus on why this is important. So this is what we try to ultimately maximize, because this is the probability of our data X, or the log probability. And we want, X is the observed data, so we want this to be as large as possible. Now remember that we wrote down these types of models to just give more expressivity to our models, right? If we can write our model like this and then marginalize over Z, that becomes a very complicated, complex set of distributions that we can sort of then use. And we can easily generate from it because we can draw a Z easily and then push it through this forward model here. And then we have our Q distribution now as well that we've introduced. And if you're into physics, what's interesting is that there's a clear analogy between these two terms with the free energy. So this term is like an energy, and this term is like an entropy. You can sort of see the entropy here. This is the expected Q of Q. Sorry, this should be log Q. Yeah, so I forgot the log here. So it should be a log Q here. So this is the entropy. And so energy minus entropy is free energy. So in this case, it says minus energy plus entropy is minus free energy. And what's perhaps interesting is that, energy is the ability to perform physical work, and the entropy is sort of the level of organization or information of a system. And in the 1820s, we were in the Industrial Revolution, and now we're in the information revolution, if you want. There's nothing really deep to say about why this equation mirrors this, and so don't think about it very much, but it's kind of funny maybe that there is this kind of analogy. Okay, so let's go into what variational inference is. Again, so we're gonna, let's say P is our intractable distribution here, which is this green curve. In general, it's far more intractable, because you have to imagine it's the space of, let's say, images where there's 1 million pixels, and it's some kind of manifold on which, the actual images that we observe live. If I generate 1 million random numbers, I'll just see white noise if I draw it as an image. But somehow, in this space of possible images, in this 1 million dimensional space, there is some manifold, and on that manifold is where the actual images that we observe live. So it's a highly structured, very, very complicated manifold that we're going to try to model. And surprisingly, now with these deep generative models, we can actually model that, because when we generate, we do see images that do look a lot like real images. So we first start, so we're going to try to approximate this green distribution here with this red distribution. And Q is from a tractable set. It's the distribution that we sort of can handle well. And so here's Q, and Q is then the KL divergence. I hope you all know what the KL divergence is, but it's like some distance metric between two distributions. It's not really a distance, but never mind. It's if Q and P are the same, the KL is 0. But it's certainly not symmetric. So the KL of QP is not the same as the KL of PQ. And so we're going to try to minimize this distance here. And if Q is so flexible that it actually models P, and we manage to get this down to 0, then the two distributions are the same. But typically Q is much less flexible. It's tractable, and so we're going to hit a sort of a hard barrier in some sense. We can optimize, but at some point we can't optimize any further. Okay, now if we write down this KL distribution here, then we basically get the sum over z, or the integral over z, of qz given x, and there's some parameters phi in this distribution q that we're trying to fit, times the log of p of z given x, and I've sort of written this with Bayes' rule. I've written this as x given z times b of z, and then there is divided by p of x here, but the divided by p of x doesn't depend on any parameters, and it can just be, it can be left out. It's a constant that we can leave out. And then there's the minus log of qz given x here. That's again coming from the KL. So it's like a q log p minus q log q. That's the KL. Okay, we want to minimize this objective over the parameters in q, and then we'll get sort of this q here. Okay, that's variational inference. That's just for q. That's variational inference to get the best q to fit some posterior p of z given x. But there's something else you can do here, which is very, very interesting and powerful, which is you can also learn the parameters of p of x, which is your actual sort of generative model that you're trying to learn. Right, so here we have our p of x given theta. This is the model that we're trying to learn. We then first write it out using our sort of way that we parameterize our models, which is a prior over z, some latent variables, times a p of x given z theta. So this is our this is basically our generative process, right? From going from z to x, marginalizing over z, because that's the definition of p of x. And then we can bound it, and that's called Jensen's bound. We can bound it to this object, which is exactly the same object that we had here. It's exactly the same thing as here. But this is now a bound on the log of p of x. And so it's so it's exactly the same sort of free energy formulation. It's the integral over q of z given x, and log of p of x given z pz minus log of p of q z given x. Now it's a bound, as I said, on p of x. And what's the gap? The gap is this difference, is precisely this KL between Q of Z given X and P of Z given X. And therefore, if Q is so flexible that it completely fits P, then the gap is 0, and we don't make any approximations. But typically, Q is not so flexible, and there's a little bit of a gap here, which means that we are making an approximation. And now, under this one equation here, we have an extremely powerful principle to learn both P and Q, the encoder and the decoder. So in the E step, we just look at this bound, which is this expression here, and we just maximize it over the parameters phi, which are in Q. And in the M step, we maximize the same bound over theta, which is sitting here in the decoder model and the P model. Now this is kind of amazing, I would say, because you have one expression, the elbow, and by optimizing this over phi and theta, you will get both your encoder Q as your decoder P, both at the same time. It's approximate because there's a gap. It's not, the Q is not actually modeling the posterior, but it's pretty close. Okay, so I would say expectation maximization is a hugely important algorithm. This is the simplest way I can explain it. In the statistics literature, you'll find far more complicated explanations of this. But this is all we will need for the variational autoencoder. Okay, so then there is this concept. Now that we know this EM thing, now there's this concept which is called amortized inference, which is really important. In amortized inference, we're just going to say, okay, I have my model, which is P of Z, and then a P of X given Z. This is my generative model I'm trying to learn, right? I'm doing unsupervised learning, so I'm just trying to learn how to generate images, let's say. And in order to learn it, because I have this bound here, I need this Q, and I need to train the best possible Q at the same time. But how I can do it in many ways, right? I can say for every single input X, I could train a different Q, where the parameters phi would then depend on the data point. That would be a possibility, but it would be extremely slow. So what I'm going to do is I'm going to say, well, I'm going to train one neural network that takes in the data point X as input and then predicts Z as output. So this is now a neural network that goes from here to here. It has one set of parameters for all the data points, right? But the way I execute it is by saying, okay, stick in X, run it through my neural net, and then I get the distribution of Z given X, and every data point uses the same set of parameters phi. Now this is the encoder, and the encoder is trying to do posterior inference in this model. So it's trying to compute the inverse of P of X given Z. It's trying to compute P of Z given X, but it doesn't necessarily succeed because maybe this model isn't flexible enough. And then the next step is to say, well, in this model, I could have, these lines is graphical model lingo. It could mean anything. But now we're going to connect to the deep learning literature. You're going to say, well, for each one of these lines in my graphical model, I'm going to insert a complicated neural net with lots and lots of parameters, right? So now I call this DP-phi. So we sort of go from graphical modeling language to sort of deep learning language. We're going to look at these conditional distributions, and we're going to use complicated neural networks to model these conditional distributions. So the variational autoencoder then is actually this simple model where I have a decoder going from Z to X, and I have an encoder going back, and each one of these Q and this one here, they're both deep neural networks. So I have to sort of deepify this line, and I have to deepify this line and make them complicated neural nets. And then I've used this trick of amortization as well. And basically, that's your variational autoencoder. So here is more detail. So here's a particular kind of model. Let's say I'm trying to model images of echocardiograms. So I have some latent variable Z and some prior over those latent variable Z, from which I can easily draw. I have some class labels, let's say, P of Y. I draw for a Z, I draw a Y at the top level. I then push it through my neural net. And then I predict the parameters of some distribution P, let's say the mean and the variance of a Gaussian distribution, perhaps. And then I draw a image by drawing from the P of X given Z and Y. So these two determine the parameters of this distribution, the mean and the variance. And then I have the mean and the variance, and now I can just draw my pixels here, and then I draw this. All right, so that's the generative part. And then the encoder, which is the sort of the discriminative part, if you want, it takes a image as input, as you do with every neural net, and maybe you do a convolution in neural net or something, and you go through many layers of this neural net. Again, you produce the mean and the variance of some distribution, and then you can draw now a Z given X. So you can now draw a latent variable Z given this input image X, and then maybe you can also draw a Y given Z, or a Y given Z and X, or whatever this is, right? But one is going in this direction, other one's going in this direction, and they are trying to be each other's inverses in sort of a Bayes rule kind of sense, right? So this is P of X given Z, and this is trying to be P of Z given X. And a way you can think of it two ways. Inside the EM algorithm, you can consider this as a crutch. You can think, well, I can't actually do proper EM where I have the true posterior. So I'm gonna learn my own posterior distribution to train this as best as I can using sort of EM. That's one way of looking at it. The other way of looking at it is to say, well, maybe I'm interested in this distribution, which is actually my deep neural net that takes in images and predicts class labels. And then my decoder here, I can put lots of prior knowledge in it. I can put my, the way I understand that the generative process of the world works, I can put it in here. And then by keeping this close to be the inverse of this model, I'm regularizing this model with my prior knowledge of the world. So that's kind of the dual view of this, if you want. Now, the VAE objective in more sort of detail is it's a KL between these two joint distributions. It's the distribution of, so P hat is the data distribution, and then the data distribution times the encoder. This is a joint distribution over Z and X. And there's this other, which is the generative distribution. It's P of Z times P of X given Z. And I want to minimize this KL. And if I can write it out into two terms, it's a decomposition into two terms. The first term here is the KL between the data distribution and the marginal model distribution over X. So this is if you marginalize over Z. And so the optimal solution would be to make P of X equal to P hat of X. Well, obviously it's not, this would have to be the actual sort of distribution from which the data was generated. So that will be the best we can ever do. And then there's this additional term here. And this term, if we minimize it, basically says that the Q needs to be the Bayes inverse of P. Right? So it basically says that QZ of X should be PZ of X, which is equal to PZ times P of X given Z divided by P of X. So that also makes sense, right? So we really want this Q to be the inverse of P. Okay. Okay, and then I have need to close a window because I hear some noise outside. 1 sec. Okay, so then the next step is to go into a little bit more detail about how you actually implement this. And there's some details there which are important. So if you take that bound that I've been talking about, this free energy, so here it is again, then the first thing to observe is that Q, in order to compute these estimates, the only thing we're going to require is that we can actually efficiently sample from C given X. But since this is just some neural network that predicts, we can just stick in an X and then compute the mean and the variance and then sample from that normal distribution. We can draw very efficiently samples from this distribution. So it can be a very complex distribution because we only require that we can sample from it. And that's sort of what we have to do. So this sum here needs to be replaced by a sum over samples, a Monte Carlo sum. And there's this other term here, P of X given Z, that's actually a sum over all the data points in your data set. Now that's also, too many terms for your gradient descent. So you will have to pick a mini batch of data points here and here as well. which means that we are again sampling now. We are sampling data points and we are sampling from this distribution. And so the total, okay, I already took a gradient here actually. So I took the gradient with respect to B. And one way to put that gradient is to realize that the gradient of a distribution Q is Q times the gradient of the log of Q. That's a particular rule that you can make. So, and then this gradient will actually disappear strangely, but it will go away. So this is the expression for the gradient, and I'm going to have to sample here, and I'm going to have to sample here, and then this will be sort of the Monte Carlo expression for it. It looks a bit daunting, but exactly the only thing I want you to take home from this is that there's so many samplings going on that the variance of this estimate is going to be very high. Every time I redo this, I draw new samples, these gradients will look completely different. And if you have a huge amount of noise in your gradients, you cannot effectively learn. That's maybe another really important lesson to take home. If you're trying to train in a system and your gradients are very noisy, you cannot train very well at all. And that's why this in itself, the VAE, doesn't work. So we need something to reduce that variance. And there is one trick, which is called the reparameterization trick, that really did it for us here, but many people followed up. And maybe let me just first look at this particular example here. So in this example, we're going to say, let's compute the gradient of the mean of this expression, which is basically a normal distribution with random variable z, with mean mu and standard deviation sigma, and a random variable z. Okay, so we want to compute the mean here of, so we want to compute the gradient of the mean here of this expression. And we can take this route of actually just pulling the gradient in and computing the sort of the gradient here with respect to the mean, and then rewriting it as an expectation. And then that basically boils down to saying, well, I'm going to draw z from a normal distribution, and then I have to sort of compute the Monte Carlo estimate of this. It has huge variance if you compute it. It's completely impractical. But if you do the reparameterization trick that I'll explain in a minute, then the variance is 0. There is no variance left. So this is a fairly extreme case that illustrates that if you do this simple trick, you can get rid of a lot of variance in your gradients. So how does it work? So I have my bound, and I want to compute the gradient with respect to phi. By the way, the gradient with respect to theta has no problems, but it's the one with respect to phi which has the problems. So now, if I compute that gradient, it looks like this, because I've just written the bound here again, and sort of I'm going to compute the gradient. Now, if I pull it in here, and I just hit it here, I get this thing, right? I get q of gradient log q. And that has very high variance. So what I'm going to do is I'm going to say, well, a conditional distribution here, like something like p of z given its parents, you can equivalently write as a deterministic function. You can say z is a deterministic function of its parents, of a bunch of parameters, and of some random number epsilon, where the random number epsilon I will generate exogenously. So I'll generate it separately from some distribution that I like, p of epsilon. And then I just, it has to be a particular distribution, by the way. And then I just inject it here. And then, this z, if I just make it a deterministic function of these things, where epsilon is now some number that I inject, then in fact it's equivalent to this. So if I do this, the trick is that this p of epsilon will not depend on any parameters anymore, and so I can pull the gradient through. So if I do that, then I get this. So now epsilon is drawn from some, let's say, normal distribution with unit variance and mean 0. And then I'm going to have to put this z that that's epsilon, right. So, and then I define z of s, my sample, as this deterministic function of this epsilon that I drew, and parameters phi, and then the gradient looks like this. So it's much simpler, but it's a bit deceptive because the z now depends on phi. And so, you have to pull it in here, and then here you have to take it here, the gradient, and you have to take the gradient there. Okay, anyway, this looks fairly complicated. You may want to look up some literature on this. It is actually a very important trick to know, because in practice, often the variance in your gradients is very high, and it's just very hard to train. Okay, so maybe, I don't know, well, how are we doing on time, actually? So I can't hear you, Saeed.
Sorry, we have 5 minutes more.
Yeah, so maybe I'll just stop here. So we did the VAE. I mean, there's lots of other things and flows that I want to talk about, but things always go slower than you would expect. So I don't know, how did you also have time for questions after this or not?
No.
Okay, so the 1.5 hours is a hard stop.
Yeah.
Okay, so then I guess we should go to questions now.
Okay, we have questions from Ahmad Wisnu. Can we use Euclidean distance in the latent space of trained VAE? Say that I would like to interpolate between points in the latent space and decode them to generate and get a smooth trajectories of images.
Yeah, that makes sense depending on the P of Z that you use. So if the P of Z is yeah, I think if that's I mean, I would pick equal probability contours, but let's say if you have like a uniform distribution in that space, then Euclidean distances make a lot of sense. Even if you would take a Gaussian distribution, it would probably still make some sense to do it. But I would prefer to take equal probability contours somehow, because then every image you generate will have equal probability, and you wouldn't have to go through, let's say, a region where the probabilities get like very low or something like this, or very high, and sort of to be on an equal probability contour seems preferable, because then every image has the same probability of happening somehow.
All right. There are still many questions. From Awan Chenggoro, do you have any intuition why GAN generally generates better results than VAE? I think there is a new result on this.
Sorry, why GANs generate better quality images? So yeah. I don't even, there's been a lot of research in this direction, but I would say that it has something to do with the loss that they use. But I would also say that there is now some work where people manage to generate very, very high quality images also from the VAE framework. You know, maybe one of the first one was VQ VAE, but recently there was also NVAE. So people can actually generate very high quality images also from VAEs. Although I would say there's maybe a tiny bit more blurry. It's a bit harder work to get it done. So I think we can sort of attribute this to the loss function in some sense.
Okay. Is it possible for one model to act as a generator and also a discriminator? It's like
that I think is hard, because it has different dimensions as input and output. So you can, but then it could be, I mean, it's certainly true that you could, if you do like an invertible model, which has the same number of input and output dimensions, and you could just basically, you can then use the same model as an input. I mean, I think people have even tried it, interestingly, and it worked quite well. So so you take the same model as input. It's like an involution. So you take, if you can train a model to go from X to Z and from Z to X using the same model, you train it as some kind of involution. And people have tried it, it works quite well, but you have to have models that are invertible and that go from you know, the same dimension to the same dimension.
All right. Next question from Javier. In the encoder, why do you estimate mean and standard deviation? Are they sufficient statistic?
You could do all sorts of other things as well, but in a way, for every data point X, we don't need a very complicated posterior distribution. We do think that if you condition on data, then the posterior distribution is simple, typically, not very complicated. Now, the marginal distribution, which is the aggregated over all the data points, can still be very complicated, because it means then you sum that, it's like a mixture over all the data points. The aggregated posterior can be very, very complicated still. But if you condition on a particular data point, then you hope that the latent variables are well nailed down, they're well conditioned, and that a Gaussian distribution should be sufficient in that case.
Okay. Next question from Ebuka Oguchi. Will the encoder become useless after the training?
If you're only interested in generation, then yes. But oftentimes people are actually interested in an encoder. So people do want to say, okay, take an input and then generate some latent variables given that input. Because people want, that's often a task, right? Like even classification is a discriminator task, but sometimes you also want to sort of predict properties of a system. And so often people are actually interested in the encoder as the sort of primary object of interest. So people don't, I mean, if you just want to generate, then you can dispose of it. But often people want, are actually interested in the encoder.
Learned representation. Yeah. Okay, from Lakshmi, he pointed to your slide 28, slide number 28. PN key is the same deep neural network as an encoder and decoder, right?
Yes, that's true.
Yeah. Okay. In the beginning of your slide, you are talking about white box and black box. Do you think that we can combine mathematical logic to discriminative learning?
Yeah, I don't know. So that's kind of saying that I think people are trying hard. So to use knowledge graphs and to use reasoning and logic. To embed this with and to help use it with deep learning. I think it's very interesting direction to try and explore, but I don't know how successful it is right now. But I think many people are trying to do that actually.
Okay.
So see, maybe we should finish here because it's time, and I'm also somebody's waiting for me. Also, I see.
Yes. Oh, that's all right. Of course, we can continue tomorrow. So for your second talk. So thank you very much for the great time in the discussion. We will continue again second talk tomorrow. But today is also the closing for the ICO DSA. So there is a closing statement from our vice rector of Telkom University. So please, Bu Rina Puji Astuti.
Okay, I have to stop. Yeah, I stop sharing now, right?
Yeah.
Okay. So I have to log off because somebody's waiting for me. But
yeah,
I'll see you tomorrow again.
Okay. Yeah. Thank you.
Okay. Bye-bye.
Bye.
Bye. Thank you, Prof. Max Willing. Thank you very much.
Yes. Thank you.
Okay. Bismillah. Okay, well, good evening, ladies and gentlemen. I believe that during these 2 days, all of us have obtained a fruitful discussions in the International Conference of Data Science and its Applications, ICODCSA 2020, whose main theme relevant to data science and computational linguistics and information science. We have learned a lot from the keynote sessions delivered by the amazing 3 keynote speakers who have shared their interesting work, especially from Prof. Max Willing. Thank you, Prof. Once again, on behalf of the committee and our rector of Telkom University, thank you for delivering such important materials so that all of us can deepen our knowledge about free energy and deep learning research. Furthermore, I would like to thank all presenters and participants who have joined this conference from all over the world. I am certain that every presenter has presented the applications research relevant to the data science, computational linguistics, and information science. I sincerely hope that throughout your presentations and discussion afterwards, all of us can contribute to solving the real problems in our own countries. Even though the contributions may be small, but it is still valuable. Finally, I would like to thank all the committee members for organizing this conference and ensuring that it proceeded smoothly. I would like also to apologize for any inconvenience that you might experience during this conference. Ladies and gentlemen, there is a saying in bahasa Indonesia, ada perjumpaan maka ada perpisahan, which means when there is a meeting, then will be a goodbye. By saying Alhamdulillah, thanks God, ICODSA 2020 is officially closed. I do also hope that we can meet again in international conference on data science and its applications, ICODSA 2021. Thank you very much. Please, Pak Said. Okay.
All right, thank you everyone, participant of ICO-DSA, and also for the MLSS participants. Don't forget, tonight we will have a practical session about reinforcement learning, again with Varial and Matt. So see you in the next 2 or 3 hours. Bye.
Thank you, Pak Said. Pakai Mas. Okay, good.
Sama-sama, Bu.
Good conference, Pak Said.
Yeah, thank you very much, Bu Dina. Pak Said also, thank you very much. Thank you very much for all the committees of MLSS and also the participant of MLSS. Thank you very much for allowing us to join with MLSS. See you later next year.
See you.
Yeah.
What makes us human is language. Through language, we convey our thoughts and interact with others. It is how we can work together to build civilizations. And as humanity moves forward, we begin creating technology. Technology that enables us to do more and make better use of language. Hundreds of thousands of years have passed, and now we have reached another pivotal moment. The rise of artificial intelligence technology, a creation that will shape our future. While some might think AI will threaten our way of life, taking over our jobs, it is not what we believe. AI can actually improve our lives. It enables us to be more productive, so we can have more time to pursue more meaningful work. We believe that AI and language is humanity's greatest creation, and combining their power will unlock a new possibility, enabling better interaction between human and machines to create a limitless future. At Kata.ai, We harness the power of language and AI to help businesses create better interactions with their users. This mission has inspired us to democratize AI technology for everyone, so you can do more and be more. Help you do everything in a better way. Do it better than today. Do it better than your competitor. Do it better for your customers. Do it better for meaningful connections. Do it better in an intelligent way. Gata.ai, understanding conversation, humanizing interaction.
The new Kata Platform 3.0 brings the most advanced technologies for your chatbot development. It is designed to make your development process even faster and more delightful. In this new version, we combine the fundamental features with uncompromising performance. These powerful tools come with great capability to help you do more. For the first time, Kata Platform has a new project system. We bring together all key features in an integrated system for a seamless workflow. Along with CMS Studio, now you can manage the content of your conversation in an easier way, enabling everyone in your team to update the content without the help of developers or coders. But that's not all. We will also have new modules coming to the platform soon. It will combine not only bot flow and natural language model, but also content management system. These features can ensure you spend your development time on what really matters, ultimately speeding up the time it takes to build your conversational interface. No matter who you are, a developer, a professional, a student, or an AI enthusiast, Kata Platform 3.0 is ready to turn your biggest ideas into your greatest chatbot.
Kata Hack Week ini adalah event 3 hari yang dilakukan oleh tim research, product, dan engineering dari Kata AI. Di sini kita terbagi atas 11 tim yang diberi kesempatan untuk membuat inovasi baru menggunakan Kata Platform. Dari 11 inovasi ini nanti akan dipilih 5 yang terbaik. Dari 5 yang terbaik tadi akan kita godok lagi sampai keluar satu pemenang produk inovasi terbaik yang akan kita garap lebih serius. Jadi alasan pertama, kita ingin memberikan waktu khusus untuk teman-teman bisa berinovasi dan berkolaborasi di antara divisi-divisi yang ada di dalam Kata.ai. Nah, nomor 2, hasil dari kolaborasi dan inovasi tersebut kami harapkan bisa menjadi produk-produk baru yang nantinya bisa kita kembangkan di Kata.ai untuk membantu pengguna-pengguna kami bisa men-solve problem mereka dengan artificial intelligence yang kami bangun sendiri.
Halo, nama saya Amanda. Di sini saya dari tim Hub bersama Yai sama Reload. Di sini saya mau bikin sebuah bot event. Kita provide CMS-nya dan kita provide botnya juga. Di sini teman-teman bisa masukin keyword untuk speaker dan untuk stage-nya dengan mudah. Dan dijamin botnya ini bakal bisa berguna banget untuk event sama workshop.
Halo, saya Adri dari tim C bareng Made sama Gali. Kita lagi bikin produk namanya katalog. Tujuannya dari katalog ini buat showcase buat kreator supaya bisa dilihat sama orang-orang, khususnya para AI entusias.
Halo, kami dari tim I yang beranggotakan saya, Mamas, dan Mas Adit. Jadi kami sedang membuat sebuah bot yang bernama Jaja, singkatan dari Jajan Asik. Bot ini bisa memberi suggestion makanan atau minuman yang disukai oleh user.
Halo, saya Rizian dari tim A, isinya Pak Go dan Mas Bagus. Waktu Hack Week kemarin kami bikin fitur namanya kata generator. Fungsi utamanya adalah untuk membantu orang manfaatin teknologi NLP lebih cepat dan lebih mudah.
Sebenarnya kita tidak melihat kata .ai itu sebagai chatbot vendors, tapi kita melihat sebagai kata .ai itu adalah Artificial Intelligence Partnernya Indosat. Kata .ai itu tidak memberikan service hanya berupa software. Dia jualan teknologi, dia jualan solusi, tapi dia juga kasih advice, dia kasih solutioning. Mas, kalau lo punya challenge kayak begini, kita advice kayak begini. Nah, that kind of consultation, that kind of service itu nggak ada di tempat lain. Terus kita juga berhasil improve, kita punya operational level. Di operational itu akhirnya kita bisa automate 30% dari total interaction di customer engagement, which is that saving a lot of investment. Chatbot is not just about chat automation. It's all about how to integrate customer data and then give a relevant and interactive digital experience ke sisi customer.
Bank Rakyat Indonesia akhirnya memutuskan untuk menggunakan layanan chatbot dalam melayani nasabah mikro yang jumlahnya puluhan juta. Mereka sudah sangat familiar dengan menggunakan messaging, khususnya di WhatsApp. Oleh sebab itu, Bank Rakyat Indonesia memutuskan menggunakan layanan Sabrina tadi di channel-channel messaging, khususnya seperti di WhatsApp dan di Facebook Messenger. Bank Rakyat Indonesia sekarang memiliki channel-channel baru yang lebih cepat dalam melayani nasabahnya kita, sehingga khususnya nasabah mikro dapat dengan cepat untuk berinteraksi dengan Bank Rakyat Indonesia tanpa perlu pusing bagaimana Bank Rakyat Indonesia memposisikan dirinya untuk masuk ke era digital. Dengan layanan berbasis AI, kita mendapatkan keuntungan dari cost reductions. We believe we could do it better with the help of AI.